So here is a picture of like the membrane, right? Or the mitochondrial inner membrane. Okay, so we've got complex 1, complex 2, complex 3, complex 4, etc., right? So I want to discuss briefly the reduction potentials of these various complexes that I just erased. So if I tell you, for instance, that the reduction potential of complex 1 is 1.0 volts, what do you know that the reduction potential of complex 3 has to be? And assume we can only use integers. Can't use like 1.1 or 0.9.
Like, well, it has to be greater.
Yeah, why is it got to be greater? You're right.
Because why does it have to be greater? Because it has gone through like 2 reductions now.
Okay.
Essentially. So.
All right. So yeah, so whenever
Okay.
complex 3 and complex 1 react together, because they kind of do, they in a redox reaction, right? Complex 1 passes an electron to complex 3. Then which one of these is the cathode? Which one's the anode between complex 1 and complex 3?
Complex 1 would be the anode. Complex 3 would be the cathode.
Okay, yeah, for sure. So if the reduction potential of complex 1 is 1 volt, what is the oxidation potential of complex 1?
-1.
Yeah, -1 volt. Okay. So if we're looking at the E of the overall reaction, in order to be spontaneous, E has to be greater than 0, right?
Oh, so it has to be greater than 1 anyways in order to counteract the oxidation potential.
Exactly. So that's the point that I'm trying to make here. Exactly. So it has to be greater than 0. And so if this one is -1 volt, then we know that this has to be something that's bigger, right? So, and then that's why I told you only integers. So 2.0 volts, right? And so the E of the cell could end up being 1 volt. I made these numbers up, FYI, but the
That's
trend
totally
is,
fine.
yeah, the trend is what matters, right? That
Okay.
that the reduction potential of each subsequent complex has to be greater. Right.
Okay.
Okay. So then what about the reduction potentials between complex 2 and complex 1? Does the difference between those two reduction potentials matter at all outside of their relationship to complex 3?
Not fully understanding why, but I'm gonna assume not,
Right.
because they would be much smaller than the 1 to 3.
Yeah. Well, 2 and 1 both pass their electrons to 3, right? So
Oh,
2
right.
and 1 are going to have similar reduction potentials just because they both have to be less than that of 3 because they're both passing their electrons over to 3.
Wait, so they're passing their electrons to 3.
So they're both using CoQ to transfer those electrons to 3, but the point is that they don't transfer between each other.
Okay.
Yeah. And I don't really go into the details of this stuff very frequently, like the CoQ, sulfur, sulfur groups, FMN, all of that stuff.
Yeah.
Yeah, just because that's just like memorization stuff that's very, very tertiary to the point of the test. Like if that stuff is going to be on the test, it's probably going to come from a passage.
Right. Okay.
Yeah.
That makes sense.
Yeah. So what I care more about is just like the big trends, because that's the stuff that they really care about testing you on. They're never going to ask you to tell them whether there's an iron sulfur group in some subunit or whatever. Like that's just not the way the MCAT asks questions. Yeah. So okay. So what would happen to NADH levels if we inhibited complex 2?
Well, my initial reaction was that they wouldn't be affected because complex 2 deals with FADH2 and FAD, but that needs to happen in order for like the next NAD DH to be reduced to NAD plus.
What does?
Like the citric acid cycle isn't finished at the point in which the enzyme of complex
Okay.
2 continues. So it would be reduced, but there's like 2 other steps before it that also produces NAD.
Yeah, there's 2 different perspectives from which you have to consider this, and you're doing that right now, right? Because you're thinking about the citric acid cycle, the complex 2 and citric
Right.
acid cycle. But then you also think about it from the electron transport chain perspective. So
Right.
so you have to think about it both from the using up of NADH and the creating NADH. Okay. So let's think about those 2 separately really quick, and then we can talk about how they work together.
Uh-huh.
So if you look at it, just because we have the electron transport chain right in front of us right here. So let's say we're coming in and inhibiting complex 2 right here. So complex 2 doesn't work anymore. All right. Well, first of all, you're going to have a bunch of FADH2 build up, obviously.
Right.
Right.
Because it doesn't just dissipate.
Right. Yeah. Okay. So you've got FADH2 build up. You also have now you're not able to transfer electrons from 2 to 3, right?
But you still have 1 able to transfer electrons to 3.
So you're still transferring electrons from 1 to 3, and 1 to 3 is going to be this reaction that looks kind of like this, where you've got like complex 1. Let's say that these are the electrons, like this little star thing. That means it's reduced. Okay, so that's like complex 1, right? This. Okay, so you've got complex 1 reduced plus complex 3 not reduced. Is that going to be at an equilibrium with complex 1 oxidized plus complex 3, which is now reduced, right? So I just moved the electrons over from 1 to 3, right? Over here the electrons are on 3, over here the electrons are on 1. This is just the reaction of transferring electrons from 1 to 3. All right, so now that I've inhibited complex 2 and I can't transfer electrons from complex 2 over to complex 3.
Yes.
Think about what I just did to this equilibrium. Well, since I can't transfer electrons from complex 2 to complex 3, what I did was I took this and decreased it dramatically. Because now it's only getting electrons from one thing. Yeah.
Oh, okay.
So because I did that, I shifted my whole equilibrium this way, meaning that I'm going to start using up more NADH than I was before.
Oh, okay.
Yeah,
And you're
so
making less on the other side too.
Yeah, and so levels of NADH are going to drop dramatically if you increase complex 2.
But if sorry, I'm still thinking about the citric acid cycle. If you're stopping complex 2, does the citric acid cycle just never finish?
Yeah, so you're going to have a big time buildup of stuff, like you're going to have a ton of succinate buildup right there.
Right.
Yeah. So you're exactly right. It would back up the citric acid cycle really badly.
But it doesn't stop the citric acid. Like it doesn't stop. It just keeps making up to that point.
Yeah, it's gonna start making stuff up to that point, but then once succinate builds up, then you're gonna shift your equilibrium, and so succinyl CoA will build up too, and then alpha ketoglutarate will also build up, and then isocitrate will also build up, and then citrate will build up, and then acetyl CoA will build up, and then oxaloacetate. Yeah. So.
But at that point, right? There's like, I remember it's not like in the middle of the citric acid cycle per se, but or maybe I'm remembering other metabolism reactions, but there are like things that tell it to stop eventually, or does it just keep building up?
Well, you're gonna get in a really bad situation, basically, is what's gonna happen. Like it's gonna be very poisonous. And like other mitochondria in the same cell, because each cell has multiple mitochondria. And each mitochondrion actually is gonna have multiple complexes. So if you inhibited all of complex 2 in your body, you'd just die. So that's
sweet. Okay.
Yeah. But if you're just inhibiting a small amount, then the rest of them will make up for it.
Okay. Cool.
Yeah. I was just wanting to think about like the immediate implications, because inhibiting any of these things has really crazy downstream implications that we can't really predict. There's just too many moving parts there.